All right, let's jump right in. Today, we're basically going on a detective mission, a hunt for the secret architecture, the hidden shape behind a very specific kind of error. You know, the kind that shows up when you're sure you did everything right.
I mean, you know that feeling, right? Where you followed all the steps in a recipe perfectly, but the cake is a complete disaster. Or you've run some code in what seems like a totally logical order, but the output is just nonsense. It really feels like a glitch in the system.
Well, it turns out that feeling isn't just a feeling. It has a name. It's called path dependence, and it is a deep, fundamental issue that scientists and data engineers are constantly wrestling with in everything from quantum physics to building more reliable AI.
So this whole problem of path dependence, it all comes down to sequence, to order. And to really get to the bottom of it, we've got to start with the big mystery at its core, the order of things.
Just think about it for a second. Putting on your left sock and then your right sock, you get the same result as doing right then left. The order doesn't matter one bit. But putting on your socks, then your shoes, that's a totally different outcome than putting on your shoes than trying to put on your socks. So the big question the research we're looking at today asks is, why? What is the fundamental difference? Why does order sometimes change everything?
To figure out why order matters so much in some cases, the source material takes us somewhere weird. It's a kind of mathematical world where our normal everyday ideas about size and scale they don't apply. Okay, this world is called projective space. And yeah, I know, the name sounds a little intimidating, but the core idea is actually really intuitive. It's a system where we completely ignore absolute size and we focus only on the relationships, on the proportions. It doesn't matter if your socks are size 8 or size 12, the relationship, socks first, then shoes, is all that matters. That's the whole idea of projective space.
And this isn't just some abstract math game. This stuff is everywhere. For example, in statistics, when a data scientist is building a model, they're often looking at the relative chances of different outcomes happening. That's a projective space. And it's the same in quantum mechanics. The state of a particle is all about its properties relative to everyone else. It's a world built entirely on relationships.
Now, inside this strange world without scale, that feeling we talked about of ending up in the wrong place gets a fancy technical name. It's called holonomy. It's the actual measurable gap, the leftover error, that pops up when you take a journey that is supposed to bring you right back where you started, but for some reason it just doesn't. This is our target. This is the glitch we're hunting.
So how in the world do you hunt down a holonomy? Well, the researchers behind this work did something pretty brilliant. They set up a kind of controlled experiment inside this projective space, comparing two very different kinds of paths to figure out exactly where that glitch is coming from.
Okay, now this slide, this is the absolute core of the whole experiment. On the left, we've got what are called commuting actions. That's like putting on your socks. Left, then right is the same as right, then left. The algebra T1, T2 equals T2, T1 is just a mathy way of saying the order doesn't matter. And look at the path it traces. It's a perfect square. It closes. No gap, no error. Simple. But then look at the right side. These are non-commuting or braided actions. The order here is crucial and irreversible. That path traces a hexagon, and do you see that? It doesn't close. It leaves a gap. That is our error. That's the holonomy we've been looking for.
So here's the crucial takeaway. The simple, square-like paths where the order is irrelevant, they're totally flat. They're safe. They produce zero error every single time. The glitch, the gap, the problem we're investigating, it only ever appears when you have this more complex, braided relationship, the one that, you guessed it, traces the shape of a hexagon.
And this discovery is so much bigger than just finding one type of error. What this does is it reveals something incredibly profound about the basic nature of these glitches. It leads us to what the paper calls the atomic hexagon, the fundamental unit of all this kind of error.
So, how many fundamental sources of this error did the researchers end up finding? Dozens? Hundreds? Nope. It turns out that at the most fundamental level, there is only one.
This right here, this is the main theorem, the core finding of the paper. And what it's saying is that any path dependence, any holonomy, any evidence gap, any error you get from the order of operations in these systems, it's not some random chaotic mess. It is literally built from these tiny hexagonal substructures. Every single complex error is just a bunch of these simple hexagonal gaps all added together. To put it another way, the hexagon is the atom of this kind of error. It is the fundamental, indivisible Lego brick. Anytime you run into this problem, no matter how ridiculously complicated it seems on the surface, if you could just zoom in far enough,
you'd find it's made of nothing but these tiny, predictable hexagonal units.
Now, this is a really beautiful piece of mathematics for sure, but it is not just some abstract curiosity. This is where it gets really, really powerful, because knowing the fundamental shape of an error completely changes how we can solve problems out in the real world. So take statistical inference. When an algorithm is learning from data, the order it sees that data can create a bias, an evidence gap. But now we know that gap has a hexagonal structure, which means we can build tools to specifically look for and correct it. Same goes for AI. An optimization algorithm can get stuck because of the order of its updates. Well, by understanding these little hexagonal traps, we can design much smarter algorithms that just sidestep them. It even gives physicists a blueprint for understanding certain effects in quantum systems. In every single case, knowing the shape of your enemy is the very first step to defeating it.
So if there's one big idea to take away from all of this, it's this. That feeling of ending up in the wrong place, that seemingly random, unpredictable glitch in the system, it's not random at all. It has a shape, a simple, fundamental, and universal shape that we can actually identify and understand.
And that kind of leaves us with one last, really fascinating question to think about. If the errors in our complex algorithms and our physical models have a hidden atomic geometry, what other huge problems in our world, in economics, in biology, maybe even in our own thinking, are actually just simple shapes, waiting in disguise for us to find them?